SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. We have been discussing the geostatistical method for estimation of the quality parameters of ore body, different types of ore bodies, and we know that the diverse nature in terms of their extension, their strike, and their length, breadth, and width, and their quality, and that the quality parameters such as grade are varying in space, and we have some idea about how they vary in space, and we just saw how we could go for an estimation of the quality parameter in an ore body by using the method of ordinary Kriging, which essentially assumes the variogram to be based on a variable which is behaving stationary, based on the stationary regionalized variable, where a variogram model has been fit. So just for the sake of a bit of a completeness, we can extend, or you can see what when these calculations can be extended to regionalized variable which behave in a non-stationary way. So we know that the non-stationary regionalized variable can be described in the form that in a very simple way, that this non-stationary regionalized variable has something which we call as a drift. That means the average that is computed at any point within the spatial domain, it does not remain fixed, it varies, either increases or decreases, and we know that if we can somehow estimate or somehow approximate this drift, we can subtract the drift and get the residual, and from the residual we can compute the semi-variogram, and we discuss something about the structural analysis which is done, this elaborate process of modeling of non-stationary regionalized variable to arrive at a situation of convergence of a assumed semi-variogram and a converged semi-variogram. So that remains at the background of it. So if we just see with that background that we want to do the Kriging estimate of a non-stationary regionalized variable, which is in many of the textbooks you will find them mentioned by the name as universal Kriging. So in the case of universal Kriging, what we have, that we have to approximate the drift as a function of distance. So that means, say for example, if our drift is denoted as MP, and the most simple way of approximating the drift by considering a linear model, let us say that is our MP is alpha 1 x 1I plus alpha 2 x 2I. Here 1 represents, you may say, easting, and 2 as northing, and this alpha 1 and alpha 2 are the unknowns. So if we have to extend the calculation procedure of ordinary Kriging to universal Kriging, then we will see how we can do that. So if the extension becomes very simple logically, we have an unknown point here as P. If we have an unknown point here as P, and then we are starting with two unknowns, which is alpha 1 and alpha 2, and then if we have to base our estimation on the value of the regionalized variable at known points, then how many points we should have. So if that is, if we take 3, then 3 will have 3 lead to 3 unknowns, and plus alpha 1 and alpha 2, it becomes 5 unknowns. So if it becomes 5 unknowns, that means we need to have 5 points for the 5 neighboring points within the validity of the spatial influence, which is decided by the semivariance model semivariogram. So now let's say this is 1, this is 2, this is 3, 4 and 5. So now we are going to do the calculation or extend this Kriging method to universal Kriging, and our unknowns are now 5. We will also proceed on in the same way we did before for the punctual Kriging. So we will write gamma h11. Here also we will do the same thing. So here our yp will be equal to sigma I is equal to 1 5 wi means w1 y1 plus w2 y2 plus w3 y3 y5, and we also have the uncertainty which is inherent. So gamma h11 w1 plus gamma h12 w2 plus gamma h13 w3 plus gamma h14 w4 plus gamma h15 w5. Similarly, we will also since sigma wi is equal to 1, so we know that. So here, even if we take as 5 unknowns as w1, w2, w3, w4 and w5, so the number of equations what we are getting is more than 5. So we are involving one slack variable like before as lambda. So here it will be lambda, and then we will have something as alpha 1 x 11 plus alpha 2 x 21. Now similarly we can go on doing it up to the gamma h 51 w1 plus gamma h 52 w2 plus gamma h 53 w3 plus gamma h 54 w4 plus gamma h 55 w5 plus lambda plus alpha 1 x 15 plus alpha 2 x 25 and then we will have our w1 plus w2 plus w3 plus w4 plus w5. So here this will be equal to gamma h 1p. Similarly here it is gamma h 5p. Here it will be equal to 1. Now here this again the same formula, same principle we can use here. x11 w1 plus x12 w2 plus x13 w3 plus x14 w4 plus x15 w5 will be equal to x1p. Remember, as one before, as done before, the distances all are known because we are taking the easting and northing are known. We can for convenience take the value of the origin at 0 0, and this is x1p. Similarly, x21 W1 plus x22 W2 plus x23 W3 plus x24 W4 plus x25 W5 will be equals to x2p. So now we will see how the matrix looks like. And also as we did in case of the ordinary Kriging, the punctual Kriging, you would have noticed that this matrix that we are solving, in addition to the fact that the diagonal elements are all 0, it also is essentially a symmetric matrix in the sense that the elements which are above the diagonal and below the diagonal are also same. Let us see how this matrix look like. Gamma h22, gamma h23, gamma h24, gamma h25, 1 x21 x22. So we will write the matrix up to gamma h51, gamma h52, gamma h53, gamma h54, 55, 1 x51 x52, and here we will have x11, x12, x13, x14, x15. Then we will have 0, 0, 0, similarly x21, x22, oh sorry, we will have 1 here as 1, 1, 1, 1, 1, 0, 0, 0, and this will be x21, x22, x23, x24, x25, 0, 0 and 0. So you could see here that the diagonal elements are all coming to be 0 here, 0, and the matrix is essentially a symmetric matrix, gamma h12, gamma h21, since gamma h12 will be equal to gamma h21, gamma h13 is same as gamma h31, and here also x11, x11, x22, x22 are 21, and then here we will have w1, w2, w3, w4, w5, lambda, and alpha 1 and alpha 2. This is equal to gamma h 1p, gamma h 2p, gamma h 3p, gamma h 4p, gamma h 5p, 1 x 1p, x 2p. So essentially this actually forms the structure, the matrix for punctual Kriging, for universal Kriging. Here we see that the order of the matrix is 8 when our number of unknowns are 5 plus 2, that is 7. The number of the order of the matrix is 8 cross 8 matrix, and it can be solved by whichever method we may choose. There are many methods available for any standard matrix solution we can use to solve this matrix, and we will get these values at W1, W2, W3, W4, W5, lambda and alpha 1 and alpha 2. As a little bit of for our convenience, what we can do that like previously shown on this diagram, that if the unknown point P here, so we are essentially going with origin as 0, and this was the easting and this was the northing that we are using. Now what we could do, we could shift this 0 0 to the origin to P. So if we shift the origin 0 0 to P, then what we can get here is a situation where these values, these x1p and x2p will become 0, and there will be some of the parameters in this matrix entry will be different, but the value will be remaining the same. And in that case, we can use, or we can calculate our semivariant, or calculate the value of the regionalized variable at unknown point P by getting this, by solving for these W's. So this is the method of universal Kriging in a very simple way. There are elaborate ways that we could solve for we could calculate the drift, and also this method could be extended by fitting a nonlinear model to the drift variation, so incorporating more number of variables, like we discussed before, taking a second order or a third order equation for the variation for approximating the drift. So within this, the basic purpose of introducing this here is that even though the many of the part, like the modeling of the semivariogram, remains a very involved exercise, but a beginner can always by using his very simple ability of handling with this set of linear equations, can get a feel of how the geostatistical exercises are done, and can always work out with some example data set, and can do this exercise of getting the feel of estimating the quality parameters in the ore body. And so within this framework, this is the here we conclude the discussion on the geostatistical methods of mineral inventory estimation, and knowing that there are this can be dealt in much more detailed and elaborate way at higher levels, but one can always make a beginning by understanding these things. And within this process, there are many other many other affairs, many other points which are also very important as far as the quality estimation, or the estimation of the quality parameter in the ore bodies are concerned, out of which the most important part is the sampling, which we just briefly discussed. So with this, I conclude the discussion on the mineral deposit inventory estimation by use of conventional and the geostatistical methods, which you can always do this exercise as the examples which will be posted, and can get a feel of it and can pursue this at a higher level. Thank you.